Okay, in this problem, we're going to use the normal distribution to approximate the values of a binomial distribution problem. So here, I guess the first place you would start is to identify that this is indeed a binomial problem. So the question is, a trick coin has been weighted so that heads occurs with a probability of 2/3, tails with a probability of 1/3. If you toss the coin 75 times, answer the following questions. So it does meet all the criteria of a binomial situation. We have two possible outcomes, heads and tails, fixed probability of success, 2/3. The trials are independent, and I think that about does it. So I'm going to solve this problem two ways. I'm going to use the normal distribution to approximate the answers to B and C, and then I'll just verify them by calculating the exact value of the binomial distribution, or the binomial probabilities in this case. So before I get started, just to explain the color coding I have here, and you could actually take this, something like this, and use it as a template for any problem you do in the future. So the good thing about Excel is that when you define formulas, when you make calculations based on locations, if you change the original data, Excel will update all of the formulas. So I color code my cells yellow and blue. Yellow means it's a number I have to manually type in, and blue is it's a calculation based on a formula that Excel is going to do for me. So in this case, if you toss this coin 75 times, so this experiment has 75 trials, the probability of success is 2/3. So I'll say equals 2 divided by 3, and the number of successes I'm looking for is 46. Okay, so now I'll define Q in terms of P. So Q is the complement of P. If the probability of success is 2/3, I could say Q is equal to 1 minus P. And for P, I'll use location B3. Now you could type in 1/3, but what I like to do is set up as many cells as possible so Excel will automatically do them for me. Okay, I'll come back to these. These would be the exact values of the binomial distribution. I'll come back to that later. So first, part A, how many heads would you expect to get on average? Well, the number of heads you would expect to get on average is the mean of the distribution, or the average of the distribution. So for binomial distributions, the mean is equal to n times p. So I have already in cells, these two yellow cells here, B2 and B3, I have n and p. So for the mean, I'll say that's equal to this location for n times this location for p. So now this is saying the mean is equal to n times p, and if I change the n, if I change the 75 to, let's say, 120, it updates the mean for me. So let me go back to 75. The standard deviation also is based on these three yellow cells, or these two yellow cells in this blue one, n, p, and q. So the standard deviation of a binomial distribution is equal to the square root. So the Excel function for square root is sqrt, square roots of n, so that's here, times p, which is here, times q, which is here. So there's the square root of n times p times q. Okay, now keep in mind the binomial distribution is a discrete distribution. The normal distribution is continuous. So we're using a continuous distribution to estimate the values of a discrete distribution. So we have to use it, instead of using the number 46, because the probability of x equals 46 exactly is 0 in a continuous distribution, we'll use the upper and lower real limits for the number 46. So the lower limit would be 0.5 below 46, and the upper limit would be 0.5 above. So again, I could type in 45.5 and 46.5, but I'm going to type in a formula based on cell B5, based on where the 46 is. So this should be cell B5 minus -0.5 or -0.5. And this is cell B5 plus 0.5. So now if I use this for a different problem, if I have a different x value, Excel will automatically update all of this information for me. So now, okay, we've done part A. Part B, what is the probability of getting more than 4 heads, or more than 46 heads? So we're going to use, and I'm going to come over here and attempt to draw it out. It's a little difficult to draw on the computer screen, but I'll try it. What is the probability of getting more than 46 heads? So we're using the normal distribution, so it looks something like this. The average is 50. And we're looking for the probability of more than 46. So probability is related to area. So the area to the right of 46 is going to equal the probability that x is greater than 46. So area to the right for greater than, area to the left for less than. So now, how do we find this area? You could use the table of values from the textbook. I'm going to use Excel to calculate this area. So remember, Excel can only calculate cumulative values from the left. So negative infinity up to 46. So this area, let's see if that works. This area over here is going to be the complement. So area on the left is equal to the complement of the area on the right and vice versa. So this area that we're looking for is equal to 1 minus the area to the right. Sorry for the handwriting, it's difficult to write. Okay, so in Excel, we could calculate this guy. We could calculate area to the, or 1 minus area to the right. Yeah, so we could calculate the area to the left. So coming over here, we're going to use, since we want, let me go back to the picture. Since we want the probability x is strictly greater than 46, we're actually going to use the upper limit of 46.5. So the value x equals 46 in a discrete distribution corresponds to the bar in the histogram between the lower and upper limits, so between 45.5 and 46.5. So here's basically the bar from the histogram corresponding to x equals 46. So that's 45.5 on the low end, 46.5 on the high end. So to approximate this, we're going to look at area strictly to the right of 46.5. So coming back over here to Excel, to calculate areas, we need z-scores. So I'm going to get the z-scores for, I'm going to convert the lower x limit and the upper x limit to z-scores. So remember, z-score is equal to x minus the mean divided by the standard deviation. So we'll say equal, and in parentheses, x minus the mean, which is here, close parentheses, divided by the standard deviation, which is here. So there's the lower, there's the z-score for the lower limit of 45.5, and we'll do equals parentheses this x value, 46.5, minus the mean, in parentheses, divide that by the standard deviation. Okay, so now we have our z-scores corresponding to the upper and lower limits of, let's see if I can delete this. Oop, I don't want to do that. Well, I'll come back to Excel. So we want to find the area to the left. So for part B, we want the area to the left of z equals negative 0.857321. Okay, so for area to the right, we could, the area to the right should be equal to the complement of the area to the left. So we could say equals 1 minus, and then the formula for calculating the area based on a z-score is the standard normal distribution function, norm.s.dist. So returns the standard normal distribution. So that's for z-scores. So it's asking me for the z-score, which is this location. And then cumulative true or false, basically yes or no. For continuous distributions, we always, 100% of the time, we use the continuous or the cumulative function. Okay, so that should be the probability that x is greater than 46. We could calculate that using the binomial distribution function. So the exact value built into Excel would be binom.dist. And now Excel is asking me for number of successes. So that's the x value. Number of trials, that's n. The probability of success, that's p right here. And cumulative, so for a discrete distribution, the cumulative function means you're going to calculate every probability for every x value from 0 up till the argument, or up till, in this case, 46. So if I say 0, it's going to give me the probability that x exactly equals 46. If I say cumulative, this is going to give me the sum of all the probabilities for x equals 0, x equals 1, x equals 2, dot, 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 all the way up until x equals 46. Now I want probability x is greater than 46. So I'm going to actually subtract this from 1. I'll do 1 minus, so this is 1 minus the probability x is anywhere from 0 to 46. So the complement, which is what we want, will be x equals 47 or 48 or 49 up till 75. And we get something very, very close within 1/1000th the value of our estimate. So here's our exact value, and here's our estimate. So the first one is the exact value using the binomial distribution function in Excel. Here's our estimate using the normal distribution, and you see they're very, very close. So now for part C, let me actually close this and open it back up. Okay. So for part C, what's the probability of getting exactly 46 heads? So on the normal distribution, if we're using this as an approximation, again, here's the mean of 50, and let's just say 50. So to approximate the value of x is exactly equal to 46, we'll use, so we want to calculate this area for 46. We'll use the lower and upper limits of 45.5 and 46.5. So this is going to give us actually this portion of the normal distribution. So we want this area. We want the area strictly between 46.5 or 45.5 on the low end, 46.5 on the high end. So the way we do this with Excel is Excel could only calculate negative infinity up to a number. So we'll do the area from negative infinity up to 46.5. And then we'll subtract from that the area negative infinity up to 45.5. So we're basically taking all of this area and then subtracting off this area in red. So this is the red part, and this is the black part down here. So if we take all the area to the left of 46.5 and then subtract off the red shaded region, it'll leave us just that sliver between 45.5 and 46.5. So I'm going to come back over here to Excel. I have to do that in two steps, or two parts to my function. So I'll say area to the left of 46.5. So I'll do norm.s.dist, and the z-score is up here, 46.5. Cumulative, yes, so comma 1. So that's the total area to from negative infinity up till 46.5, and I will subtract the next area, so norm.s.dist, and the z-score I'll use is the, oop, that shouldn't be that, sorry. Sorry, let me go back here. The upper limit should be B15. That's the z-score corresponding to 46.5. And over here, for the lower limit will be over here, B14, which is the lower limit corresponding to the z-score corresponding to 45.5. Okay. So that should be the probability that x equals exactly 46. So I'll come up here and check that with the binomial distribution function on Excel. It's actually easier to calculate it exactly than to approximate it using the normal distribution. But we should get something very close to 0.06. So I'll do binom.dist. That's the formula for binomial distribution. And Excel's telling me, you don't have to remember the arguments or the order to input the arguments. Excel's telling me exactly what to type in. So first is number of successes. So that's 46. Or I'll use cell B5. Then total number of trials. That's N. That's B2. Probability of success. That's P. So that's B3. And cumulative no. So 0 means no or false. We don't want all of the x values from 0 up to 46. We just want x equals 46 exactly. So 0.059, 0.060. So again, we're within about 1/1000th of the value when we approximate. So this looks good. Our approximations are very close in both cases, within 1,000th of the actual value. So I use two functions here. Let me just maybe go back over them. Might be helpful. So for the standard normal distribution, when I'm calculating the area to the right or to the left of a z-score, I used equal norm.s.dist, and then the arguments, you input the z-score and 1 for cumulative. So this gives you always area to the left of the z-score. And then for the binomial distribution, I use the formula equals binom.dist, and the arguments here are number of successes, so I'll say x, number of total trials, so that's n, probability of success, that's p, and for part C, I used 0. So for the cumulative function 0, or if I say 0 for the cumulative function, that means do not use the cumulative function. This gives me the probability that x equals exactly 46. And for the x greater than 46, I used the function binom dot dist, and inputs were x, n, p, and here I used 1 for the cumulative function. So what that does is that's the probability x equals 0 plus the probability that x equals 1 plus x equals 2, and so on and so on. Equals 1 plus the probability x equals 2 all the way up to the probability that x equals 46. So for the answer for B, the probability x is greater than 46. Well, Excel could do 0. Excel always works from the left. So I calculated all of these probabilities and then took the complement of that, 1 minus this sum. So that's what I have here in cell B7, B6. 1 minus all the x values from 0 to 46. That leaves me all the probability of all the x values above 46. All right, I know this was a little bit complicated, but it helps to make a template like this. So, and you could do this for any topic, any type of problem. So right now, you could use this as a template for approximating the binomial distribution using the normal distribution, and also for finding the exact values of the binomial distribution just for the cases x equals and x greater than. You could add to this if you want for the greater than or equal to case, the less than case, and the less than or equal to case. But the key to making like a nice template is have as few inputs as possible. So if I have a different problem, let's say with, let's say I'm doing a different problem with n, p, and q. Let's say n is 150, p is, or sorry, np and x. Let's say n is 150, p is 20%, and x is 32. So let's say I have a different problem, same type of problem, a binomial distribution approximated by the normal distribution. If I type in these three values manually, 150, 0.2, and 32, all of the values in Excel are automatically updated. So you see the limits, 31.5 to 32.5, the mean is down to 30, so on. Everything in blue is connected to those three cells in yellow by an Excel formula. So all these calculations are done based on the location, the yellow cell. So it's either B2, B3, or B5, not the numbers in those cells. Okay, so that does it for this one. Hope this helps.